So, welcome to our final session on aggregate data types. We in the last two sessions we already discussed enums and structs and arrays, and now in this video we will do a little bit of work to understand the relationship between arrays and pointers and look into the efficiency of an array access. Good. Now let's start with that and have a look into how arrays and pointers are related. Okay, we start with one-dimensional arrays, and well, just consider the following example. We define a variable grades, which is an array of 7 int elements, and we declare another variable, p grades, which is a pointer to an int. And we initialize p grades by the value grades. And this has to work because we already have seen several times that grades is the array, and an array specifier is nothing else but the address of the first element of the array. So these both variables fit together. Okay, now let's consider the following situation. We are for the next time we look into our memory, and the memory is illustrated as here. We have some addresses, we pick some, I don't know, this is just some values out of the memory, and you've seen we start here with FC46, and we continue with FC4A. The question is how come? Because normally we would have FC47 and so on. But in our common architectures, int values are 4 bytes long, and so we don't treat every single address here. So we just look into every fourth index of our memory. So FC4, 6, 7, 8, and 9 are dedicated to store the value 5 because it's an int value and it takes 4 bytes. Okay, now if we are so we have clarified how the memory should look like and why it looks like it is. And now we consider the following. We take grades at index I, and well, just make a very simple thing here. If we, for example, take 4, so means grades at position 4, we would say, okay, where is grades? Grades, of course, it starts here at FC46, and we have the first element, so means index 0, index 1, index 2, index 3, index 4, etc., etc. And if we consider we want to access index 4, we should end up here at FC56 and the value of 9999. Good. But now we are looking into a slightly different line of code, and let's see what comes up here. We take grades, add I, and then out of that we are fetching the value. This means here we have a pointer, grades is the pointer to the first element. When we add some value to to grades, and we treat this as an address, and then we say, okay, what value is at this address in our memory? This is the meaning of the star. Okay, just see what happens here. So we have grades. Grades has the value of FC46. Yeah, FC46. And then we add I times 4. So why this? The C compiler is checking what type do we have here. And we have an int. And now it says, okay, we have to add I, but I times 4, because an int is 4 bytes long. So if we write down this in the background, the compiler is resolving this address by multiplying by a factor representing the size of our data type. So this means basically, if we have an int, a pointer to an int value here, and we add something, it adds something times the size of the data type. Okay, just this concrete example with I being 4 as we had here. So what does it do? It says we have grades, this is FC46, plus 4 times 4. This would be 16, but 16 in the hexadecimal system is 10. 15 would be F, and 16 would be 10 in the hexadecimal system. So we add FC46 plus 10. What is FC56? So FC56, So FC56 is here. Good, so this means we have FC56 as a result of this expression here. And now we're taking the star, which means we take the value as an address and look into the memory at this address and figure out what value it is. And ta-da, we end up back again at our 9999, which is the same result here as we would get here. Okay, summarizing, we could say that so writing down here and saying, okay, I have an array and I want to access the element I, is simply the same as taking the pointer, adding I, and then taking the value at this address. So these both are the same both lines of code have the same, basically the same meaning. Of course, we take this one because it's much more convenient and we are used to that. Okay. If you now, so this is something you could try yourself. If you now take p underscore grades and do the same stuff, yeah, what will come out? This is left to you as an exercise, but this is really, really simple, of course. Good. This is now, this was the shows how one-dimensional arrays and pointers relate. Now let's go to a multi-dimensional array, and so for making our explanation simpler, we use two-dimensional arrays, and have a look how this is now working. Okay, for example, we have a two-dimensional array v of some height and width. You remember we had in the last session we had completely the same thing. And okay, we check out for some concrete values, height being equal to 3 and width being equal to 4. And yeah, how would this look like? We normally imagine such a thing as a matrix of 3 rows and 4 columns. And now, if we have something like this, we access this array. What does it mean? So it's easy here. It's row number 1 and column number 2. Row number 1 is here, column number 2 is here, so we should end up at 7. Okay, but again, have a look how this looks like in memory. And you know, memory is always a a one-dimensional array. So we don't have any matrices here. We just have one linear array of addresses and the corresponding values stored at these addresses. Again here, if we look at here, we have so 4 bytes of a distance between two addresses, and this is totally the same as before, simply because we have an int and a 4-byte int value to store there. Okay, now okay, you see sorry, you see we have these values of our matrix here. We have flattened out into a one-dimensional structure. Means the first row is the first 4 elements, and the second row is the second 4 elements, and the third row the third 4 elements. So this is just taking one row and putting it into the memory, and followed by the second row and so on. So this is how a two-dimensional structure is represented in memory. So now let's have a look. How do we again calculate or how is in the background, how is it calculated where to access? For example, if we try to figure out V at the position 1, 2 of our matrix. So have a look here. So if we should end up here, somewhere here at the 7, which is basically here, which would be FC58, and have a look how it works. We have FC40. This is the base address, or the address where V starts. And what we do now is that we say, okay, we have row number 1, and if we have some row, a full row, we have to add width, sorry, we have to multiply width by the number of rows we have to skip. So this means we have one row to skip, because we're referring to row number to the second row, which is index 1. So we say we have to skip one row. This means 1 times width means 1 times 4, and then we add the column number we want to access here, plus 2. And of course, since we have again 4 byte values here, we multiply everything times 4. So this means we have FC40 plus 6 times 4, which would be 24 in the decimal system, and if we have here in the hexadecimal system, it would be 18. 24, you see here, 8 plus 16 would be 24. So we add FC40 plus 18, and this would be FC58, which is here. And you see, it works. We can access the right element out of our two-dimensional array by doing this calculation. And if you look now into this calculation, you see we just needed width out of these two parameters. We didn't need height to calculate the proper address here to get the value. So, and now you can imagine the following, or now you can understand why we said in the last session that we don't need the height or the first dimension of a multidimensional array. We need all the others because we have to multiply by these, but the first one is not needed. Okay. Again, it's up to you as an exercise. Go through that and try to calculate how V at position 2 and 3 would be calculated, and whether you end up at the correct position in our memory. Okay. Now we have these two situations for the one and the multidimensional arrays, and now we want to go to another very so to say interesting thing, because we have a difference here between C# and C, and this means arrays as return values. Consider the following situation. We would have a function called getZeroVector, and this function accepts one parameter, namely length, and what it returns should be a one-dimensional array of length. And yeah, normally we would also in C# it would be pretty similar to that. We would declare a local variable here, and we would say new length, a new int length, and then we would initialize everything by 0, and we would return this. In C, this is a bit different, and we will look into that, and we'll see how it works. So to complete our scenario, we just say we have a main function, which is here calling a get zero vector with a length of 4, and we want to store the first the first element, or the pointer to the first element, um, into a variable v, and then we want to assign v at position 2. We want to assign a value, namely 42. So here we consider so to say pointer which shows our next instruction we want to execute. This pointer here is the so-called program counter. That's why we'll call it PC. Okay, if the program starts, it starts with the first instruction of main. So that's why PC points to the first line, and then since we call the function get zero vector, the PC jumps up to here to the start of get zero vector. Additionally to this, now we want to see how the memory looks like. So here is the memory, and so again some arbitrary part of it out of it, so we assume that it starts somewhere here now. And what we have here is another pointer, and this is the so-called stack pointer. So how does this come into our image? We say we have, our memory is just a linear array, and if we need some new memory, we take the next free address, and the stack pointer is simply taking or pointing to our next free address. So we say, okay, there is some memory even before. This is already allocated and not so important. So for example, v would be maybe before would be at fc 42 and so on. And now, but here we are. This is now the next free address is fc46, and there is some arbitrary values here. Okay, since we were calling now a function, we have to do a little bit of bookkeeping work here, because you see here we will have to return something, and this value has to be stored somewhere. So we simply allocate this address, and we say this will be the place where we want to store the return value. That's why we call it RV. Then we have a parameter, namely length. This also has to be stored somewhere, because you maybe remember the 4, this number 4 here will get copied into here. So what we do is we allocate length, store our actual parameter here into length. So we have the 4 here available in our function. Good. Then we are done. So PC is moving to the next instruction, and the next instruction says, okay, we declare a variable vector which is an array of int values, namely 4, because length is 4, so we have to reserve 4 values into our memory. So what we do is we are moving the stack pointer the stack pointer down here to have 4 addresses reserved for our vector. And of course we have to store somewhere where it starts. So we have another value somewhere else, vector. And since it starts at fc4e, we store for c4e, the start address is stored into here. Good. Then we're done. Well, next so basically the two statements here is nothing else. We are iterating over all the elements of vector and set them to 0. So this is the easy stuff here. 0, 0, 0. Good. And then we are moving down here with our PC, and here is the statement return vector. And this means in the background we are doing the following. We have vector, this is the value 4C4E, and since we return it, we have to store it up here in our reserved address return value, because the caller will then fetch the this value of RV and store it down here into our V. So okay, whoop, this thing is copied up here, and now we're done. So basically what happens now is that the main function takes RV, stores it into V. This means we will get 4C4E being stored into V here, and we clean up the memory because we don't need all that stuff here anymore, because these are all local variables. So what happens is we're moving the stack pointer back to the beginning where it was at the beginning of the execution of get0 vector, and we store the return value for C4E into V. Good. And if we move now down here, we have a problem, because there is a local variable, or so to say, we have a pointer here, V. This is 4C4E, and 4C4E is here, and then we add 1 and 2 here, two addresses, and we want to assign the value of 42 into here. But basically we could do, but the address itself is not valid anymore, because it is locally, it was made invalid after exiting this function. Would say if we call another function here, a different function maybe, which again is doing some local variables and stuff like this, again here the addresses would be taken from here, and so we would then overwrite our memory. This means we would access or we do access an invalid address. Good. So as we have seen here, it doesn't work here, because we are doing here, if we allocate the memory locally in here without any other means, then we would return an invalid address here. So we have to find a different way. You remember from our last video that because I've shown you already the way how we do it in C, because we are, maybe we'll start here with our considerations here. We are first of all, we are allocating the memory for our vector in the callers area. So means in the so to say in the stack frame of the caller. Means stack frame, we can understand something like the memory locally assigned to our function here. So but here we now have the V, and all its 10 values are now stored in main. And then we call getZeroVector with a v, with the v as a parameter, and the length of v here 10 again. And so if we call this here, then we are getting the vector v, and in our function we can iterate over all the elements, and we store the zeros into here. And this means again, you know this already, getZeroVector is writing into v by using its backlink. You should already be familiar with, as we did in the last unit, deeper considerations how arrays and other values are handed over to functions. And now, since v is still valid in here because we are still in that function main, we could safely access the value of 2, or the position 2 of v. And this is still a valid address, namely an address in main, and not as before an invalid address of the function getZeroVector, which is already history at this point of time. Good. Just to show you how it how things are now would behave if we would do it in the old way. I'll show you now in a programming session. Okay, let's go to our programming environment. We have our editor here and our shell. Let's do a bit of focus work. Yes, good. Should be fine here. Okay. Let's start and do some programming. The new file, call it init_vector_fail, because we want to show how things are really failing now. So of course we need something to write out into the shell, and we have of course a main function with an argument count and some argument vector. Good. And I show you what I want to do the following. I want to say, okay, we have a pointer to an int, and this should be returned by I don't know, init vector, and we say it should be for size 10, and furthermore we want to give it an initial value of 5, something like this. So what we want to have here is that we are if we would say we go through this vector here, and we would say printf %d or something maybe better, just to make it more explicit, element d. So we would get the index and vector of, oops, pretty sorry, no, this is nothing, so Zip I. Okay, we have a few things messed up here. Yeah. Good. Well, but yeah, that's it basically. We want to do, so what we want to do is we want to get an init vector, and we want to print out all the elements. You see here we have we need the prototype. We say okay, int star init vector, and int, this is the length of the vector, and then initial value sub. Okay, this is what we have. Copy, and this one, make it compilable. Just give it a try whether we could, oopsie, whether we are able to build the whole thing. Okay, let's go back to here. Okay, good. GCC -o init vector fail -w all pedantic -std is C99, and init vector fail. Sorry, init vector fail dot c. Okay, we have in line 9 we have obviously missed semicolon. Okay, but now it works. Good. Then we will do the correct implementation here, and here we said okay, we have we need some local vector of length here, and then we do int equals 0, oops, I smaller than length I plus plus sub here, and then we say vector at position I equals initial value, and at the end we return vector. So this is the implementation as we have basically shown in our slides. Okay, and there is one thing already because which is quite nice. Our compiler is giving us a warning, and it says the address of a stack memory is associated with a local variable, and this is returned. So it definitely does already warn us, but this is just a feature of more modern compilers. So, well, this is also a reason why never ever we should ignore any warning, because these are very, very important hints where we could have a problem. Just give it a try. So we already compiled and linked that thing, so we could call it. Okay, this is not so nice written here, but you see that we have already only zeros. No, we have a 4, a 0, a 0, a 0. Okay, just do the following to make things a little bit better readable. No, we are now doing this one again, getting the warning. Yes. Okay. And you can see already that although we were assigning initial value, which was 5, to every element here, we only have the first element, right, and all the others are back again 0. Yeah? So this means uh, because we had called here another function which was taking uh, the unused or the values or the memory before used by init vector, we're getting some messed up values. Things would get even worse if we are maybe typing something like this and saying we call print vector, and sorry, this is the vector and some and its length here. So what we do here is that void print vector int sub vector v and some length sub, and we implement this here. Good. And we move all that stuff out of here and then to here. So just some refactoring work to make the main function better readable. We say we call print vector, and we are length. Good. We are doing the printing here in this function, and oops, I'm pretty sorry. How did it here? Good. Use of undeclarative, yes, of course, because we called it vector and not v. Okay, good. We are back, still ignoring our warning because we want to show that the warning has some real serious background. So, but a warning simply doesn't say it is. A warning says, okay, it's a warning, but it is generating code. The compiler is generating machine code. So we could start here, call, and you can see now here even more the now here things are pretty strange, because we have the first value is okay, then we have some other value, then we have 2 zeros, then we have other values, etc, etc. So things are very pretty messed up here if we do this. Good. This is what I wanted to show, and this is I also refer back to session 2, where we have shown, or where I've shown you how the C way is to the C style is to initialize and to handle arrays. Namely, the caller has to provide the memory, and we have to pass the memory over to our subfunctions here. Okay. Good, that's it. We are going back to our presentation. We are now nearly done. We have only one very tiny thing I want to show you, and this is the efficiency of an array access. This means how much time does it take to access one element of the array. And so this one, already, so means that if we write down here grades at position I, this is the same as if we would write down grades plus I, and we take the value of this resulting address. So, and you can now easily see that it doesn't depend if grades has 5 elements or grades has 500,000 elements. It's simply always the same. We just have to do one addition here. We have to add either 5 or 500,000 to get, for example, the last element. And this is one addition, and this takes constant time. And so this means here we don't, array access at this point is pretty efficient because it is totally independent from the number of elements stored in our array. If you somehow consider another situation, okay, here again, size of the array doesn't influence the access time of its elements. If you compare this to another scenario where we say, okay, I want to find one element having a specific value. So, for example, I want to have the first element having a grade having a value of 1, then we have to go through all the elements and check whether it's for each index here we have to check whether the value of grades is 1. And in the worst case, if this is only the very last element, then it depends if we have 5 elements or 500,000 elements in our array. Because if we have only 5, we would go we would have to iterate 5 times over that array and if we have 500,000 elements, we have to do it 500,000 times, and then we don't have constant time to access. Then we would have linear time to access, which would be O of n here. Okay, this is just to give you a first idea how we are considering efficiency of algorithms, and you have seen here that we are writing this down as we have here O, a big O notation. Sorry, here we have the big O notation. This is called like this, and we say, okay, if we're just taking constant time, doesn't depend on the elements we have to check, then we write down O of 1. And well, we will see in the next session somewhere we'll see different O's, and we will see also O of n and O of n square and stuff like that. Okay, good. We are through. Just to summarize what we did today, we repeated how arrays and pointers are related. You know, it was how we calculate in the background which address is of some index, or how to find an index by calculating its address. Then we had this funny problem with the stack pointer and the invalid address, and that we can't do it in the C# way, at least not directly, as we could imagine here, because we have invalid addresses. And finally, we checked out the efficiency of array accesses. Okay, that's it for this session and also for this unit. So we finished Unit 4 now, and yeah, I hope things were clear to you. The explanations made sense, and if you have any comments or troubles or other remarks, feel free to post them in the comments down there. Okay, thank you, and hope to see you soon at Unit 5.